pulses are nothing thus far. Okay. Now, let's see what happens when we run a 0, 1 through there. Okay, let's see if we get the same result. So this is going to be 0, 1, which is the third permutation. You guys already told me that as long as one of these is false and is false, this 0 runs through the P. Okay? So this time when I run 0, 0 through OR, since neither of them are true, you have false or false, you have to pick false, and a 0 through a NOT gate negates it to a 1. Okay? So now we finally get some sort of output that has an impulse turned on for this. Okay? We could do the exact same thing with the last ones. Okay? So this time I'm just running a 0 through. Okay? And I think it's going to work out to be the exact same thing, right guys, for that as the previous. A 0 and a 0 gives a 0. We trace the 0 through. The OR through the 0 is a 0, and then the output's a 1 for this. Okay? So, this is the most fundamental thing that we have to make sure that we can do with circuits. Okay? You basically have to know what the circuit's going to do. If you don't know what the circuit's going to do, why even try to build anything with it? Okay? Does that make sense, guys? Any questions? Ma'am, please.
Actually, the diagram with the P and the Q and the way that it is, that part doesn't kind of make sense. So is a P and Q going into AND?
That's correct.
P and Q going into OR?
What's happening is these two right here, the zeros are going through the AND. And see this, since this was initially a 0, this 0 is also following this impulse as well. So what's happening with this?
So I guess I understand the logic, but I don't understand the diagram. So is P and Q, are they both going into OR as well?
Like
Yeah, that's
you're going down too.
No, it's not connected from.
Oh no, this is just connected at the P. Okay?
Yeah.
So it has nothing to do with the Q. So it might be helpful if it looked like that, where there's just a dot where it's soldered onto that first
Yeah, I get
part.
it.
Okay, does that help now? Okay, so basically, because I can't draw it in 3 dimensions, I could have drawn it, I guess, like to go out that way. Does that make sense now, ma'am? Okay.
You can kind of see it in the second diagram.
Right, yeah, I did a better job on that one.
The Q will.
Yeah, this one's directly connected to that. Okay, so sorry about that. I'm not trying to confuse you guys, at least not on purpose. Okay. All right, so what I'd like for you guys to do, if you haven't done it already, go ahead and take a few minutes and see if you guys can come up with the input out to the table for the second of these. Okay, so this is the first question I'm going to ask you guys to do on assignment number 2. So now's a good chance for you guys to get some practice. Okay, and while you guys are doing that, I'll try to pull up an application as to why we even care about this stuff. Yes, sir.
How
Please.
come P has just 2 1s and 2 zeros instead of 4 1s and 4 zeros?
Because there's only 2 inputs for the entire thing.
Oh, okay.
If it was a P, Q, and then an R, then you would have 8 rows. Okay. And you know what? Even if you did that, you still get the same. You still get the same results. You just have double the results. Okay. So you basically be duplicating something. Does that make sense, sir?
Yeah.
Okay. Good. Because remember, it's always 2 to however many power of however many inputs you have, or in this case, however many basic statements you have. Okay? It's a good question. Because most of the stuff we've had has 8 in it. I'll give you guys another minute to finish up, and then we'll go through the answer. so let's go through the solution to this to make sure that we're all okay with this. Alright. When I do this, okay, just for efficiency, and eventually for some of you guys that aren't too good with this, you'll get to like seeing this after doing repetition. I always look for obvious cases of things that don't work. Okay, then I go for other stuff that I think might work. Okay? Guys, isn't it pretty obvious that this is connected with an and? If this guy's a 0, isn't the whole thing false no matter what? So what combination would give us, or what permutation, excuse me, would give us a 0 as the output automatically without doing much thought? 0, 0, right? Because guys, if you put a 0, 0 through here, it doesn't even matter about this garbage. 0, 0 gives a 0 here, which means that this is going to be a 0 no matter what. Okay, so that makes things really easy for us. Okay, so at least we'll cut down at least 25% of our stuff. Okay, but if you don't see that right away, not a big deal. You can still bully it and get what you want out of it. Okay, if I put 2 1s through the gate, now from now on, I know no matter what I put through here, it's always going to be a 1 for the other 3 of those inputs, right guys? Because at least as long as one of them's a 1, then this is going to be a 1. So if I throw 2 1s through here, 1 and 1 is 1, we get a knot of 0, 1 and 0 is a 0. Correct guys? Okay. Now, the good news is when I start throwing either a 1 or a 0 through there, that's when we're going to start getting the 1s as the output for this, okay? Because if I put a 1 and a 0 through this, that's going to be a 0. A 0 negated is a 1. And remember, this is always, no matter what we do, whether it's 1, 0, 0, 1, or 1, 1, that's always going to give us an output of 1 no matter what. Okay? So it looks like that if you put a 1, 0 through, it's going to end up being a 1. And wouldn't it be true is if I flipped those around and got 0, 1, then it would also be a 1. Okay? This is a specific type of circuit that some of you guys might already know the name of this thing. Okay? Does anybody know what type of circuit this is actually called? Okay. This is something called an exclusive OR. Okay? So this guy right here, or girl, don't want to be gender biased. This is an exclusive OR. Okay? An exclusive OR means that the only way that you get an output is if you have one of them false, one of them true. Okay? This circuit is actually used quite often when you're building breadboards or building other things in the computer, okay? Because you don't want both, you want basically to say, if they're the same input, whether the impulses are on or off, I want that to be false. The only time I want it to be true is if one of them is true, okay? Usually in computer science, I see this as the exclusive OR. Okay. So, for those of you guys that are going to take like a secondary course, and most of you guys probably are in computer architecture, you might see this where there's a line behind it, okay? That's actually the shorthand for writing an exclusive OR, okay? And believe it or not, they actually make circuits that are condensed versions of these things, just to make it easier because they're so frequently used, okay? Like for instance, you guys remember the number 2.71819 da-da-da-da-da? That's what number? E, right? But we don't write 2.71819, right? We write E because it's convenient. It's the same thing. It's just more convenient to write all this garbage as this. Okay? Alright, let me show you guys like why you would ever want to know anything about a logic gate. Okay, so I found these pictures on the, and you guys don't see these for any reason. Some of you guys might have worked with something called a half adder, and some of you guys might have worked with something called a full adder. Okay? When a computer, and we're going to see this later, it might not be today, but it might be on Monday. But when a computer does operations, okay, remember, computers only work on 1s and 0s, only ons and offs. It doesn't know anything else. Okay? So if a computer wants to add 2 numbers, it goes to binary, right guys? And the binary, what happens is that it uses an exclusive OR for the sum when you add 2 binary numbers, and then it uses a carry for the output, okay? So like for instance, okay, let's say for some reason, and this is in binary, okay? If I add 2 1s together in binary, that's not 2, right? Because binary only has 1s and 0s. Does anybody know what the output for 1 plus 1
1,
is in
0.
binary?
1, 0.
1, 0, right? Okay, so there's a carry. So 1 is the sum, and 0 is the carry, right? Well, what happens is, when you throw this through, okay, you throw a 1 and a 1 through an exclusive OR, okay, so that's sum, they might have flipped that around. Oh, I'm sorry, I flipped these around. So this is the carry and the sum, I'm sorry, I dyslexiated it. So, sorry. This is the carry, and then this is the sum. Okay, because obviously you carry over. So let's say for some reason you guys threw a 1, 1 through a half adder. 1 or 1, or 1 or 1, and gives you the exclusive OR of 0. Okay, so this would be a 0. But if you throw a 1, 1 through a half adder, that's a 1. So in binary, when a computer adds 2 bits, and remember, or 2 impulses if you would, that's how it gets 1. That's how a computer understands addition. Now that's only 2 bits, right? We want the computer to be much more efficient, which is why we go from half adders, which is just this part, and if you guys notice, the full adder is actually comprised of these 2 components right here, okay? So half adders help us to comprise the full adder, and what a full adder does is it actually adds 2 binary numbers together, okay? So, and just think about this. This thing's ugly, okay? Like if I asked you guys to compute an input-output table for this, you guys could do it, right? I mean, you'd sit there for about maybe 5 or 10 minutes. That'd be a pain in the ass, but you guys would do it, right? But that's what the computer has to do. Now think about this. It only adds 2 numbers at a time. How many things does a computer do at once? Like when you guys are playing any sort of computer games, it does trillions per millisecond, right? Think about how much that would have to do for us. I mean, it would take us 5 minutes just to construct an input-output table for this. Think about running that trillions of times. Isn't that just amazing? I mean, that is to me. I know I'm all happy about it, sorry. But it's just amazing to me how a computer can run things so much quicker than us, okay? And when I say us, I mean human beings. Now, what can a computer do? A computer can't think logically, at least to some extent, okay? Like they have artificial intelligence, and then they do the Turing test and all that crap, but that's different, okay? So to me, it's just really cool. So anyway, bottom line is, I'm sorry, before I start going off on like some euphoric tangent, that these things are really applicable. They happen in real life. Every single one of you uses this every day. You turn on a light, you use a half adder. You start your car, you look at your internet, okay? It's all half adders at some point. Okay, so I just want to make you guys aware that this stuff is used somewhere in real life. Okay, so blah, 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 blah. All right, one of the things that we want to make sure of is that if we have a Boolean circuit, okay, I like to be able to construct either, there's 3 things that we can think of with Boolean circuits, okay, so, or 3 different forms. And you guys don't have to write this down, because we're going to see it no matter what. We have a circuit representation, we have a table representation, but then we also have a Boolean expression representation. There's 3 different ways that we can express Boolean circuits, or 3 different conversions, if you would. So there's circuits, there's tables, and then there's the expressions. Okay. We can go from any one of these at any time. In fact, that's what we're going to be focusing on for most of today. If I give you a circuit, you should be able to construct a table and construct an expression. If I give you an expression, you should be able to construct a table and construct a circuit, okay? So that's what we're going to work on today, is converting back and forth between the 3 different ways that we can express a circuit. Okay, so let's go ahead and construct a Boolean circuit or Boolean expression for each of the above. Okay, so I'm going to go back up. I'm just going to put them on the board so that way it's easy for you guys to see. And then I'm going to erase all my hieroglyphics up here. Okay. The way that I think about this is I think of order of operations. I start from left to right, okay? And if there's any parentheses per se, that's how I do it. Okay. So, the first thing I see is I see a P and a Q. I'm going to write P and Q. Okay, I don't think I can go wrong with that. And what I'm going to do is I'm going to put that in parentheses. Okay. The next thing I see after the and is I see an or that's connected to a P. So I'm going to say P and Q or P, and then I'm going to put that in parentheses. And then the last thing that I see is I see a NOT gate. So finally what I'm going to do is I'm just going to put a NOT at the end here. Okay. Now, one of the things you guys, and by the way, if you gave me that, that's perfectly fine. But I want you guys to take a look at those Boolean laws that we looked at that you needed for homework. Okay? I bet you we can simplify this circuit. Because sometimes what happens is we get circuits and they're not always the most efficient circuits. Okay? Look inside the parentheses, guys. Okay? Is there anything that I can do to simplify what's in the parentheses? Oh, I see what you mean, like factor it almost. Unfortunately, I think you might be on the right track, Don, okay? So, say it one more time, maybe I just didn't understand.
Can you take out the keys from those things?
Okay, unfortunately not. That's if you had like two sets of parentheses, could you factor the P out? Okay, sir?
The absorption law?
You can actually use the absorption law, okay? I think does the absorption law have the P first and then the Q?
Yeah.
So actually what we can do is we can flip these around. Okay? So this is fine, by the way, guys. But notice if you flip around the order by using a commutative law, doesn't this turn into not P? And that's just by using the absorption law. Take a look at the truth table, guys. Doesn't the truth table say that when P is true, the output is false? Doesn't the truth table say that when P is false, the output is true? So really, guys, does it matter what Q is in this example? Doesn't matter, right? If we were somebody that's in the government, well, let me rephrase that.